Alright, so today we're talking about matrix operations, or operations with matrices. We want to be able to add, subtract, and apply a scalar to them. So a matrix is a rectangular array of numbers that's enclosed in brackets. It's used for data analysis. Dimensions of a matrix is the number of rows by the number of columns. So remember, rows go side to side. So these are the rows and these are the columns. So a 3 by 2 matrix has 3 rows and 2 columns, is what that's saying. Each value in a matrix is called the entry, and each entry has its own location called the address. So A, little subscript 1, 3, is in row 1, column 3 of that matrix. And in order for them to be added or subtracted, they have to have the exact same dimensions. And then a scalar is a number that's multiplied by a matrix and is distributed out to all the entries. So in our first example here, we're looking at prices for various passes to go to the theme park. And we have 1 day, 2 day, 3 day, 5 day, and then you have basic, super, and deluxe. So maybe we're going to Cedar Point or Six Flags or something. So if we want to display the data in a matrix, matrix is just the rectangular array of the data in here. So I'm just going to fill these numbers in, and I'm going to leave them in the exact same order that they're in. Okay, so the dimensions of P, so we name this matrix P, are rows by columns. So I have in here 1, 2, 3 rows and 1, 2, 3, 4 columns. So this would be a 3 by 4 matrix. On part C, what is the entry at P31 and what does it represent? So P31 means third row, first column. So if I look in here, third row is here, first column is here. So that means 80. 80 is the entry that we're looking, and what does it represent? It represents a 1 day deluxe pass. So what is the address of 120? So here's 120 in here. So that is the second row and the third column. So that would be P23. And part E, write an expression that represents a matrix that shows the cost of buying theme park tickets for a family of 4. So if your whole family is going, all of these prices would be multiplied by 4. So that's when a scalar comes into play. I would say 4 times P. So that would take this 4 and it would distribute it out to everything in there. And then it would give me the cost for my whole family. Alright, example 2, we are adding and subtracting and adding scalars on here. So the dimensions of A is our first question. So again, how many rows and how many columns? I have 3 rows and 2 columns. So that is a 3 by 2. Which entry is at B22? So I look in matrix B. I want the second row and second column. So that would be that 1 right there. A plus C. When you're adding matrices, we said at the beginning that they have to have the exact same address, which they do. Or sorry, not address, dimensions. So when you're adding them, you simply add the corresponding entries. So I'm doing like 2 plus 1 is 3. Negative 2 plus negative 2 is negative 4. 3 and negative 2 would be 1. 0 and 5 would be 5. That would be 2, and this would be negative 3. So you add them just the exact way that it would make sense to add them. Part D, A plus B. So if I look at A and B, these do not have the same dimensions. This one was a 3 by 2, and this is a 2 by 3. So since they don't have the same dimensions, they can't be added. So I'm going to say undefined. And then 3a minus c. So I'm going to do 3a first and jot that down. So 3a is taking a scalar and applying it to everything in here. So I'm multiplying everything in there by 3. And then I'm going to subtract c from it. So be careful when you're subtracting and you get these double negatives and whatnot in here. So 6 minus 1. Negative 6 minus negative 2 is like negative 6 plus 2, so that's going to be negative 4. 9 minus negative 2 will be 11. 0 minus 5 is negative 5. That would be 6 and 10. Alright, so take a look at the last two there using these matrices from up here and answer those two questions. And your joke of the day, where do kittens go on their class trip? They go to the Meowseum. All right, have a wonderful day and make sure you're kind to someone today.